Chapter 5 deals with gases. It's the third property of matter behind solids and liquids, and this whole chapter is dedicated towards that third phase of matter. So one thing about gases, some fundamental properties of them are, number one is that they diffuse. So diffuse is another way of saying they spread out. So if you open up a gas in a room, it's going to fill up that room and lock all the doors and lock all the windows. The gas will essentially dissipate or diffuse throughout that room. So essentially they spread. As part of the intermolecular attractions that gas molecules have, they're very weak. So usually when a gas molecule reacts with another gas molecule, they have an elastic collision. That means they will just bounce off each other. And they can also bounce off the walls of the room. They can bounce off the walls of the container that houses the gas. So essentially, if you look at the third point here, the particles move all around and bump into each other. So there are several variables that describe the behavior of gases, and they are, number one, pressure. So you can imagine a gas that's housed inside a container, and it's diffusing around, moving around, it's hitting the wall, and it's hitting each other. So this would be a situation where the pressure of the gas inside this container would be very high. If you contrast that, if I just simply increase the size of the container and have the same 4 gas molecules, would be less interactions, a less statistical probability of the gas hitting the side of the container. So this would be a situation idealized by low pressure, P, and this would be high pressure, P. So that's one property that we can describe the behavior of gases. Pressure. Number 2 is volume, and volume is usually in V. You actually see that here as well. Under high pressure conditions, you actually have a low volume, and under low pressure conditions, you actually have a higher volume of occupancy of the gas molecule. So volume is another metric that we use to describe behavior of a gas molecule. The third behavior is the number of moles. That's usually designated by N. So you can have a lot of moles of gas, or you can have a little bit of moles of gas. Remember, the moles has 4 definitions, and we can describe a gas molecule by the number of moles we've had. So you can have so many moles of oxygen gas. You can have so many moles of carbon dioxide gas. The fourth property that we can use to describe gas is temperature. And for all gas law equations, the temperature must be in Kelvin. So P, V, and NT are 4 methods, are 4 properties of gases. A gas will have a pressure, it will have a volume. Actually, we say a gas exerts a pressure, so it could exert a high amount of pressure or a low amount of pressure. A gas could occupy a certain volume. A gas can have a certain number of moles as its quantity. And then a gas behaves according to the temperature of the system. So if you raise the temperature of a gas, obviously certain things will happen. One of the things that will happen is that the molecules actually dance more. They expand, and they have an increased tendency to react with each other. So there's an increased ability for these elastic collisions, and there's an increased ability, if you increase the temperature, there's an increased statistical probability that it will hit the sides of the container. So we can unify all of these gases by one equation, and that equation is called the ideal gas law. Ideal gas law is PV equals nRT. This sort of a unifying theory that encapsulates the pressure that a gas can exert, a volume that the gas occupies, N is the amount of gas you have, T is the temperature. Remember, the temperature must be in kelvins. And all of this is unified together by this universal gas constant R. And this gas constant is 0.08206. Its units are liters, atmospheres per mole Kelvin. So this will be given to you. You do not have to memorize this. This is one version of the gas constant. There's another version as well that we'll talk about later in this class. So some interesting relationships that exist between the pressure, volume, number of moles, and the temperature. P is the pressure that usually is expressed in atmospheres. That is a unit of pressure, but you can also see other units of pressure pop up. One of them is called millimeters of mercury. The torr is another unit of pressure. So just be aware of, cognizant of other units of pressure, particularly millimeters of mercury, torr, and then also there's the Pascal. But for the ideal gas law that's going to utilize this version of the gas constant R, you're going to want to have your pressure in atmospheres. The important thing here is that the temperature has to be in Kelvin K. It cannot be in degrees C and it cannot be in Fahrenheit. If you notice in this equation here, temperature T, if that temperature was in degrees C, and you have, let's say, a temperature of minus 20 degrees C, that minus goes all the way to this side and it becomes PV equals minus nRT, and all of a sudden you have minus N. There's no way you can have minus the number of moles. So in order to get rid of the fact and to avoid the fact that you cannot simply have a negative value for N, because you cannot have a negative number of moles, you cannot have a negative quantity of a substance, we usually express temperature T in Kelvin. But let's say if I have V as constant, N as constant, R will always be constant at this value, and I divide by T, I can get this relationship. P1 over T1 is equal to P2 over T2. So this relationship actually is what's known as a direct relationship. So as the pressure goes up, let's say you increase the pressure from P1 to P2, they will have a new T1 that will be higher. So as the pressure goes up, the temperature goes up. Obviously, this situation occurs if your volume and the number of moles remain constant. R will always be constant. Let's look at another relationship here. Let's look at the relationship between pressure and volume. So if I hold N as constant, R as constant, which will always be constant, and the temperature T is constant, I'll have P1 V1 is equal to P2 V2. This is an example of an indirect relationship. This is also known as Boyle's law. Imagine compressing a cylinder so that its volume has decreased by this much, and you can see as you decrease the volume, there's less space for these four gas molecules. So the propensity for elastic collisions and the statistical probability it's going to hit another gas molecule or hit the wall of the container will increase. So this is a situation where you would have more pressure, obviously because the volume has been compressed. This would be a situation where you have less pressure. This is known as Boyle's law. Let's look at another relationship where we keep our pressure constant, our temperature in Kelvin constant, and we have V equals N. We'll divide by N and we'll get V1 over N1 versus equals V2 over N2. This is known as Avogadro's law, and it also expresses a direct relationship. This expresses a direct relationship. As your volume goes up, your number of moles goes up. Think of inflating a bicycle tire. If you're inflating a bicycle tire, you're inflating it with air. And what's going to happen to the volume of that bicycle tire? Well, it will inflate, so hence it's going to increase in volume. So this is known as Avogadro's law. There's another one known as the combined gas law, where if we take PV and divide by NT, that would be a before condition, and our after condition would be PV equals NT. So the combined gas law would look like this. Over N1 T1 is going to equal to P2 V2 over N2 T2. Right, so this relationship is basically the same as a combination of all of these relationships. It's a combination of P1 over T1 equaling P2 over T2. It's a combination of V1 over N1 equaling V2 over N2. And it's a combination of P1 V1 is equaling to P2 V2. So this is called the combined gas law. One relationship that I forgot to mention amongst these three relationships was the relationship between volume and temperature. As you can see here, it's going to be V1 over T1 is equal to V2 over T2. So this is an example of another direct relationship. As you increase the temperature of a gas, the volume of that gas will increase. So you should know what is a direct relationship versus an indirect relationship. And you should know the ideal gas law. Probably the most important thing is that the temperature has to be in Kelvin. See the relationship between pressure, volume, and temperature by utilizing this popsicle stick figure. So if you hold the temperature constant, put your finger over the temperature T, and if you raise the pressure, what's going to happen to your volume? The volume is going to decrease. What happens if you raise the volume? Pressure will decrease. Right, let's hold pressure constant. If you raise T temperature, which has to be in Kelvin, what happens to the volume? The volume increases. If you keep the pressure constant and raise the volume, what happens to the temperature? The temperature increases. So these are all the different properties of gases. So let's hold as a final example volume V as constant. So if you hold volume V as constant, if you raise the pressure, what happens to the temperature? It goes up. Both of them go up, so that's a direct relationship. And what happens if you hold the volume constant and if you raise the temperature? What happens to the pressure? The pressure also goes up, so that is a direct relationship. So really here, P, T, and V are three variables. We have a situation where you have one indirect relationship, volume versus pressure. As one goes up, the other goes down. As the other goes up, the other one goes down. As we stated before, this is the ideal gas law. It sort of combines all the laws together, Boyle's law, Charles' law, Avogadro's law, all the combined gas law, they all come together. R will be furnished to you on an exam, so you really don't have to worry about it. But let's think about a very important condition that's derived from these laws, and that is STP, which stands for standard temperature and pressure. So first off, you have to realize that this is a very specific set of conditions. Now, the second thing is, what are those exact conditions that typify STP? One is the temperature. So the temperature has to be at 0 degrees, but remember, we can never have degree C in the ideal gas law, so we have to immediately convert that to Kelvin. A temperature of 273 K, so that's your standard temperature. Your standard pressure is going to be 1 atmosphere. These are the conditions, nothing more, nothing less, that identify and are associated with standard temperature and pressure. We know our exact standard temperature and pressure. Our standard pressure at STP is 1 atmosphere. Our standard temperature at STP is 273 Kelvin. So what is the volume of 1 mole of a gas? Now the key word here is 1 mole. I'm not saying 2 moles or 0.5 moles or Avogadro's number of moles or a million moles or 1 times 10 to the minus 6 moles. It's just 1 and 1 mole only. What is the volume of 1 mole of the gas under these conditions of 1 atmosphere of pressure and 273 Kelvin? So let's put it into our ideal gas law, PV equals nRT, and let's solve for V. So V is going to equal to nRT over P, and now we can put in our conditions. N, as we predefine it, is 1 mole of a gas, an ideal gas. R is 0.08206 liters atmospheres per mole Kelvin. And T is the temperature at 273 Kelvin. And then P is the pressure, which we have defined as 1 atmosphere. So looking at our units, atmospheres and atmospheres cancel, mole and mole cancel, Kelvin and Kelvin cancel. You're left with liters. We have 1 mole of a gas, 0.026 liters per atmosphere per mole Kelvin is R. Standard temperature is 273 K, and the standard pressure is 1 atmosphere. Moles and moles cancel, or atmospheres cancel, or Kelvin cancel, and we're left with units of liters. So when we plug that into our calculator, get a value of, so N is 1 mole times 0.08206 is the ideal gas law times T 273 divided by, we have a pressure of 1 atmosphere, and we get 22.4, and our units are in liters. Our volume of 1 mole of a gas under STP is 22.4 liters. This is a number that you should memorize. The volume of an ideal gas is at 1 mole at STP is 22.4 liters. So what are the implications of this? It's a very quirky thing of nature. So imagine if I have 1 mole of SCO2, or 1 mole of O2, or 1 mole of F2 gas, fluorine, diatomic fluorine. Here's diatomic oxygen that we breathe. Here's carbon dioxide that our body expels out. So, or if I have 1 mole of this strange gas called UO2, or if I have 1 mole of nitrogen gas, whenever gas I have, its volume is still going to be 22.4 liters. So what's strange is that 1 mole of CO2 we know has a molecular weight of 44.0 grams per mole. But 1 mole of it at STP will still have 22.4. It will still occupy 22.4 liters. 1 mole of oxygen gas, 32.01 grams per mole. Well, if I have 1 mole of oxygen gas at STP, it still will occupy 22.4 liters. If I have 1 mole of F2 gas, fluorine gas, so that's roughly around 70.01 grams per mole. If I have 1 mole of fluorine gas, STP, it will still occupy 22.4 liters. If I have 1 mole of uridine dioxide, this strange gas that has a molecular weight of roughly 240 grams per mole, 140 grams per mole, that's huge. Well, 1 mole of that at STP will occupy what volume? You're correct if you stated it was at 22.4 liters. And 1 mole of nitrogen gas. 1 mole of nitrogen gas occupies 8.1 grams per mole. So 1 mole of nitrogen gas at STP occupies what volume? 22.4 liters. So regardless of molecular weight, whether you can have something very heavy like UO2, or you can have something very light like nitrogen gas, which should just float up in air, if 1 mole of that gas, any gas, no matter how light or no matter how heavy, it will have a volume of 22.4 liters. And that is the volume of 1 mole of a gas at STP. Let's do some practice problems utilizing the ideal gas law. Calculate the volume in liters occupied by 2.12 moles of nitric oxide at 6.54 atmospheres and 76 degrees C. So 2.12 moles, that would be N of this gas, nitric oxide. P would be 6.54 atmospheres, and T would be 76 degrees C, but we cannot put our temperatures whenever we're dealing with gases in degrees C. We have to put it in Kelvin. 273 plus 76 would be this value in Kelvin, and that would be 340 Kelvin. And what are we being asked? We're being asked to identify or compute the volume. So we have all the variables necessary to plug this into PV equals nRT. So let's go ahead and do that. PV equals nRT. We are asked to calculate the volume. So volume is going to equal to nRT over P. So let's put all our variables in. The number of moles is 2.12. Put the units in, moles of NO gas. R is the universal gas constant, 0.08206 liters, atmospheres, mole Kelvin. And then T is going to have to be in Kelvin, so that's 349 Kelvin. Divide that by P, and P is 6.54 atmospheres. Checking our cancellation of units. Checking our cancellations of units, atmospheres and atmospheres cancel, Kelvin and Kelvin cancel, mole and mole cancel. We're left with liters, so 2.12 times R, 0.08206 times 349 divided by 6.54 will yield 9.28 liters. You have everything here to just plug in straight into the ideal gas law. This question asks, what is the volume in liters of 49.8 grams of HCl at STP? Next question asks us, what is the volume in liters of 49.8 grams of hydrogen chloride gas at STP? So remember, STP is standard temperature and pressure. So what's standard temperature? That's 273 Kelvin. What's standard pressure? An atmosphere. So you have two variables there that are needed to answer the question in terms of volume. So what is N here? Okay, so is the volume going to be 22.4 liters? The answer is no, because we do not have 1 mole of HCl. We have whatever this mole is when we convert it to moles from grams. So don't get confused. It's not 22.4 liters. That would be a wrong answer because it's not 1 mole. Ideal gas. It's not 22.4 liters. So let's convert this grams to moles, and that will give us number of moles of N in N. So 49.8 grams of HCl. We know that for every 1 mole of HCl there is, H is 1, 30, Cl is about 35, so there will be about 36.01 grams of HCl. 38 moles of HCl. Exactly 1 mole, so it's going to be not 22.4 liters. It's not the ideal volume for the ideal gas because we don't have 1 mole. But what volume will we have? So let's go back to our PV equals nRT. All for V. N this time is 1.38 moles of HCl. It's going to be 0.08206 liters atmosphere per mole Kelvin. R will be given to you. You do not have to memorize R. T has to be in Kelvin, and at STP that's 273 Kelvin. And then P is the pressure. Pressure at STP is nothing more than 1 atmosphere. So you're really going to have to know these two conditions of STP. Standard pressure, 1 atmosphere, standard temperature, 273 K or 0 degrees C, but we always put our temperature in Kelvin anytime you're dealing with the ideal gas law. Let's check our units. Atmospheres, atmospheres cancel, Kelvin, Kelvin cancel. Mole of HCl cancels with moles of HCl, and you're left with the final units of liters, and we're being asked to identify the volume. 30.9 liters. So 1 mole of an ideal gas will occupy 22.4 liters, but 1.38 moles of HCl will occupy 30.9 liters. It's not 1 mole. If it was 1 mole, it would occupy 22.4 liters, but we have 1.38 moles at STP, so it's going to occupy something other than 22.4 liters. Number 3 mentions a sample of oxygen gas initially at 0.97 atmospheres. So if you have that initially, that word initially should be a buzzword, and it should basically tell you that you're going to be utilizing one of those derived equations, whether it's Charles' law, Boyle's law, or Avogadro's law. So it's initially going to be at 0.97 atmospheres, is cooled from 21 degrees to minus 68 degrees C, a constant volume. So it's asking what is the final pressure. That's actually a mistake on my notes. And should be asking you what is the final pressure in atmospheres. So that word initially is one buzzword, and the other buzzword is final. So if you see initially and final, realize that you're going to have to use one of those relationships, the sort of the ratio. And in this case, it's going to be the relationship between pressure and temperature. So what is that relationship? It's P1 over T1 is equal to P2 over T2. We have our P1 at 0.97 atmospheres, T1 at 21 degrees C. We have to convert it to Kelvin, so that's going to be 294 Kelvin. 2 is going to be, well, that's what we're trying to solve for. What is the final pressure? And T2 is going to be minus 68 degrees C, but we have to convert that to Kelvin. So in doing so, we get a temperature of 205 Kelvin. In cross multiplication, we can solve for P2. 2 is going to equal to 0.97 atmospheres, 205 Kelvin, divided by 294 Kelvin. Kelvin cancel, and you have 0.97 atmospheres times 205 Kelvin divided by 294 Kelvin. Well, no pressure is going to be 0.676 atmospheres. When the temperature goes down, what happens to the pressure? It also goes down. Problem number 4 talks about a gas that's initially, there's that buzzword again, initially. So that should ring bells. We're going to have to use one of our relationships here. Initially at 4 liters, 1.2 atmospheres, and 66 degrees C undergoes a change. Okay, that's another key word here. So that the final volume, okay, final. So initial condition and final condition. And final volume and temperature are 1.7 liters and 42 degrees C. What is the final pressure of the gas? Again, we're going to utilize one of those laws. In this case, we're probably going to use the combined gas law because we have more than 2 variables whose relationship we need to decipher. So let's go ahead and see what we have here. We have V1, we have P1, and then we have T1. And now we have a V2 and we have a T2, so we have to solve for P1, a new P2. So PV equals nRT. PV equals nRT. One of the combined relationships is P1 V1 over T1 is equal to P2 V2 over T2. So we can start filling in our P1, which is 1.2 atmospheres, 1 which is 4.0 liters. Our T1 is 66 degrees C, but again, please convert it to Kelvin. 2 is actually what we're trying to solve, so P2 is going to variable. V2 is, where's V2? 1.7 liters. V2 is going to be 42 degrees C. Let's go ahead and convert that to Kelvin. And then we can use cross multiplication to solve for P2. So solving for P2, we get 1.2 atmospheres times 4 liters times 315 Kelvin divided by 339 Kelvin and 1.7 liters. This gives us an answer of our new pressure, which will be, notice the cancellation of units. Kelvin cancels out with Kelvin, liters cancel out with liters. We're left with atmospheres.